that happened to me once because I was on Instagram because I was never there. And then I think someone hacks your account and you don't even know it. So, yeah, you can tell how much I like social media if that happened to me. But I guess you can't lump them all together. Facebook is different. Okay. Although this topic is really maybe a little bit challenging, I feel like for whatever reason, maybe the notes were just flowing, but I feel like I was able to get the point across really well in my last class, which bodes well for you guys because there's always an improvement in the second class. So I don't, I think we're going to be just fine. All right. So I want to, all right, let me do a slight recap from Wednesday's online class video, okay? So what you need to be comfortable with and what I would recommend this weekend is taking the simulation, so this guy here, and probably looking through the real molecules to start, and you can always come over to the model and build them however you want. But using that simulation in combination with this table, I think it's 11.1. Yep, it's in section 11.3, this table 11.1. And make sure you understand what we mean by each of these terms, electron groups, which of those electron groups are bonds, which of them are lone pairs, and then how do we use that to name the electron geometry and the molecular geometry, how that influences their angles, and not just the names, but today you'll see that visualizing what that name means becomes really important. So the stuff we're talking about today, polar molecules, you have to be able to visualize the molecule in order to understand how polar bonds are going to interact with each other in a given molecule. So when I say tetrahedral, I want you to be picturing this shape, right? I don't want you to just know that if something has 4 bonding groups, 4 electron groups, 4 bonds, that it's a tetrahedral. I don't want you to just repeat the name. I want you to be able to visualize this because the name's only going to get you so far. Okay? All right, so summary of this table, just in case you need a recap. Each segment is the number of electron groups, single bond, double bond, triple bond, lone pair, that surround the central atoms. We're always focusing in on the atom that's in the middle there. That number of electron groups tells you the name of the electron geometry. All that means is the name that we give for how the electrons surround that central atom. And if there's a lone pair, the electron pair still takes up a region of space. So if we go back to our simulation, it's still tetrahedral the way that the electrons are arranged. Okay, so electron geometry is completely defined by the number of electron groups. Molecular geometry then has to kind of trace the shape of the atoms themselves. The electron pair, the lone pair, affects the shape, but we don't look at it, we don't visualize it when we say the name of the shape. So the molecular geometry here is trigonal pyramidal because those atoms make a pyramid shape. The lone pair is there, but we're not thinking about it in the shape of the molecule. It's just influencing the shape of the molecule. So I do not want you to just like straight up try to memorize this chart without any context. It's virtually impossible to do something like that and actually get it right every time, okay? So what I want you to do is practice through the simulation, come up. A lot of these molecules are already in that real molecule selection tool, but go through each one of them, make the molecule, visualize it, and confirm to yourself why it's called the name it is, what its angles are, okay? And eventually, by the end of today, you'll also be able to determine if that molecule is polar or not, meaning if it has a difference in charge. The only other thing that I didn't mention was the angles. Just keep in mind the predicted bond angle always comes from the number of groups. So if you're talking about any of these, where the electron pair geometry is tetrahedral, then the predicted geometry is going to be 109.5. I can't even hear a can open anymore without being like, I need a Diet Coke. It's like a Pavlovian response. All right, so go through those this weekend and determine if you need a list of the things you're looking at. I think it's at the very end of this notes. Oh, no, that's not what I wanted to. I guess you could look at this exam topics. So you're going to be looking at electron geometry, molecular geometry, bond angles, polarity. The only topic we will not have covered by the end of today is hybridization, which is looking at how do we model the orbitals in bonding. We talked about it in atoms in last semester, but now we need to look at it in molecules, okay? So I would highly encourage you guys to go through, do lots of studying on all of these other topics. If you haven't done it already, do a first pass on the questions for the Chapter 10 practice exam. And then do all of the homework you can for Chapter 11, because the exam is on Friday of next week, so 1 week. So you want to use the weekend to kind of catch up, make sure you're fully up to speed on everything, so that all you need to do next week is that 1 day of new material on Monday and then studying for the exam the rest of the time. That's your most likely way to be successful. Okay. So back to the notes for today. Nope, that's the wrong one too. There we go. Okay. All right. So that table is going to be a good help for studying. But when you get into the exam itself, you're going to have to be using this table here that's on the exam equation sheet. So it's very helpful if you've already studied with the simulation, with the table from the textbook, and this can kind of guide your memory on the exam. And obviously the shapes, the molecular shape names are on there as well. But this isn't, you can't just use this. That's not going to be adequate. Okay, polar bonds. This is also a review. We did this in Chapter 10. We talked about what do we mean by a bond being polar. So we first have to look at the difference in electronegativity. And the bigger that difference is, the bigger the difference in charge between two atoms. So all we've done so far is kind of look at it like this. So if we've got chlorine and hydrogen, chlorine's 3, hydrogen's 2.1. And so there's a difference in charge because the electrons spend more of their time over by the chlorine. If we had HF, fluorine's 4 and hydrogen's 2.1, or maybe it's 2.2 on your sheet. So there's still a difference in charge. It's just a bigger difference in charge. So I'm going to draw those partial signs bigger to indicate that. I'm totally making up these numbers, but maybe it's something like negative 0.7 and positive 0.7. And maybe for chlorine, it's more like negative 0.5 and positive 0.5. Okay, so there's still a difference in charge for HCl. It's just not quite as dramatic as HF. This is just 2 atoms, though. 2 atoms, really straightforward. We just have to look at the difference, and whichever one is more electronegative, that's where the negative sign will be. There is a way that we kind of simplify and represent drawing this difference in charge, and this is very much a physics topic. They're called vectors. Yes, okay, so if you've done physics recently or you're really into it, you'll remember this. But a vector is a way to indicate in this case, a direction and how big or a magnitude of a particular difference in charge. We use vectors for a lot of different things. In this instance, we're using it for a difference in charge. And we give it this name called a dipole moment. Dipole meaning polarity. Think of it as tied to that. So this little arrow here is to represent a dipole moment or a difference in charge. The size of the arrow represents how big that difference in charge is. And the arrow starts with this little positive side and then points towards the negative. So if you had HF, you would still have the same direction. It would follow the bond length, but the size of that arrow would be bigger. It would be longer to represent that the difference in charge is bigger. So it's a little bit simpler of a way, especially once we start to get multiple bonds within a molecule. It's really the only way to easily represent that difference in charge. Okay, that's not totally true. We can still use the partial signs, but it's a good way to start at least. Okay, so when we look at vectors, these arrows that have a particular size and direction, it's important we understand kind of how they work. If we had two of these vectors that are the same direction, so think of like a number line. So X and Y, this is like our 0 point. Okay, if they're both pointing in the positive direction and we add them together, they're going to be additive. They're going to be plus 10 in that particular direction. Let's look at example 3 first, and then we'll go back to 2. If we have two that are in the same size, the same magnitude, they're both 5, but one's positive and one's negative, then they're going to cancel each other out when we add them together. They're going to kind of null out each other's effect and have an overall effect of 0. And then similarly, if they're opposite directions, but one is bigger, so this wouldn't really happen. I'm trying to think of an example. No, that's not very good. Let's just pretend that we've got carbon and fluorine versus carbon and chlorine. Okay, so negative because it's pointing, because the bond is going that way, but it is less polar than the fluorine one. Some of it cancels out, but not all of it. There's still an overall dipole moment or an overall difference in charge. Okay, so how does this apply to molecules? We're going to first look at a molecule that looks like example 3, where they cancel each other out. So CO2, if we just think about the CO bond, carbon's 2.5, oxygen's 3.5. So there's a difference in charge there. The oxygen's more electronegative. So as you can see in the blobby picture over here, you're going to get partial negative charges. Oh, sorry, we're just looking at the first side of the molecule first. You're going to get partial charge on the negative on the oxygen and positive on the carbon. So we can represent that with one of these arrows pointing towards the oxygen. So this would be like carbon monoxide, just CO. But CO2 has two of these bonds, same size, but they're in opposite directions. So here's the big thesis statement. If you have a polar bond, but you have an equivalent polar bond in the opposite direction, the molecule will actually not behave like it has any partial charge. Okay, so I've shown this one as having partial charge on the two sides. negative charge on the two sides and a positive charge in the middle, it will not behave like that. It will behave like there is no difference in charge at all. A formal way of saying that is that there's no overall dipole moment. So this one isn't a great example, but no, I'm going to do a different one. I came up with another one. All right, let's look at beryllium. And we've looked at BeF2 before. Let's substitute in a bromine instead of the fluorine there. Okay, so going backwards, carbon's like 2.5, boron's probably 2, and beryllium's probably 1.5 is my guess. Now don't freak out because, yeah, technically we would expect beryllium to form ionic bonds. It's weird. It sometimes does this underfilling thing like we showed the example, and it does form covalent bonds. It does share those electrons, okay? Fluorine is 4.0. So it's actually a big enough difference. We probably should categorize it as ionic, but we don't for whatever reason. So this is a very large dipole moment pointing towards the fluorine. Big difference in charge. Bromine, yeah, I think that's right. It's about 2.8. Remember, you have a table of these. You don't have to keep them in your head. So there's still a difference in charge, but it's significantly smaller. So what is that? 2.5 and 1.3. So not quite half. Okay, so they're opposite directions, but the difference in charge, the size of that dipole moment is different. And so some of it will cancel out, but not completely. Okay, so maybe this and this cancel out, but you're kind of still left with this amount of charge difference. So if everything cancels out, like in CO2, we say that it behaves like there's no difference in charge. Behaves as no difference in charge. Or we call that molecule nonpolar. With the beryllium, fluorine, bromine one, because it doesn't cancel out completely, we would still say that the molecule itself is polar. All right, are we okay up to this point? All right, these are just linear molecules. So this one's pretty straightforward. They're just straight across from each other. What happens when we have something that has lone pairs on it? Usually this is Y. It has lone pairs on it, and those end up offsetting the two bonds. So to remind us of what water looks like, no, I want those. Want one less of those. Okay, this is water. Still has two bonds, but it also had those two lone pairs. And so the two bonds were offset. They kind of took a different geometry into that bent shape. So they're no longer directly across from each other. So oxygen and hydrogen do have a difference in electronegativity. It's about 1.4, I think. But the two bonds are not positioned in a way to cancel each other out. So it still maintains that appearance of having partial charge. So polar bonds, but because of the geometry, so maybe I should write that down too. Because of the molecular geometry, they can't cancel out. So the molecule will be polar, meaning it appears to have these partial charges. Those still influence how it interacts in the world. And thank goodness, because this is one of the things that makes water so unique and, you know, is why we're alive. Okay, so I will show you this addition thing like we showed in that previous slide. I'll show you that one more time for this one so that you get that vector addition works even if they're not directly across from each other. But this is probably the last time I'll show you that. That is really just if it's useful for you. After I do this, we're going to talk about a little less, way less technical of a way to think about it, but that will work and help you to identify these molecules. Hopefully you're seeing too why it's so important to be able to visualize what the shape is, because that influences whether these bonds will cancel out or not. Okay, I think this is from geometry. I don't really remember, but if you remember, if you have a line that you have on like an X and Y graph, it has an X component and a Y component.
Slope?
It's like the slope, yeah. If you look at these two, they are like they're directly across from each other, okay? They're actually pointing this way. So this one would be minus and this one would be plus. But they're the same size and they're pointing opposite directions. So these parts will cancel out. Those parts or components of the dipole moment. But the Y parts are going to be additive because they're both pointing up. So that's where this dotted line comes from. It's trying to show you what the sum of those two dipole moments is. Those components cancel, so it's just straight up and down in the middle of the molecule. Like I said, if you are more comfortable with the math, if you are more physics, engineering oriented, that might be really helpful to think about it that way. The problem is once we get into 3 dimensions, nobody wants to be adding up X and Y and Z components of vectors. So we're going to talk about a way to think about how do we know if these dipole moments will cancel out. So I like to use the example of a tug of war, or the analogy of a tug of war. So think about carbon stuck in the middle. It's got 2 ropes tied around it. And the oxygens are on the outside, straight across from each other, pulling. They're pulling because they're the strong ones, right? Oxygen is electronegative, and so it's pulling on that carbon. But there's another thing that's just as strong as it, pulling on the other side. So there's no clear winner in this tug of war. We would call that nonpolar. That charge doesn't actually have a preferred side. It just kind of cancels itself out. For the beryllium example, you have a similar situation. They're right across from each other, but you've got the fluorine, which is stronger. And so bromine is going to kind of resist the other side, but not enough. So the fluorine is going to pull those electrons way more, and the molecule would then be polar. So it can't completely cancel out the efforts of the fluorine, but to some degree. Water's a little bit weird. You can still think of the external atoms as the ones doing the tugging. In this case, it's actually oxygen. That's the one that is strong. Either way you think of it, though, it still is going to give you the right answer. So let's think of the hydrogens as the ones doing the pulling, even though they are less electronegative. So they're tugging this direction, but there's nothing to counteract them on the other side. And so there's definitely going to be a difference there, because if they were tugging down, the molecule is going to shift, or the electrons are going to shift. Now, in reality, it's the oxygen that's tugging on the electrons. That's fine. It still tells you that there's a difference in charge. But the whole point is that that tug of war idea lets you see if those efforts, if those tugs are going to be able to cancel out or not. So you have to first have an accurate Lewis structure, then you have to think about the geometry of the molecule, then you can consider whether they cancel out or not. So I think I wrote that down at some point. I'll write it down here. So gotta have a Lewis structure first, then you can think about the molecular geometry. Then you want to look at the polar bonds. And the strength of those polar bonds, or magnitude, the size, like how polar they are. This is not really in order of priority. You're probably going to want to do this first, just because why wouldn't you? And then you kind of want to, using that molecular geometry, you want to ask yourself if they're able to cancel each other out. You could look at the bonds first and see, are they polar and are they equivalent to each other? But like, you're going to have to go to the molecular geometry after that anyway, so. All right, so this table kind of summarizes a couple of the examples we've already done. CO2, water. This could also be something like SO2. Remember, SO2 has a lone pair and two groups surrounding it as well. So it's bent, but it's bent at 120 instead of slightly less than 109.5. Either of those would behave the same way. They've got a polar bond, but those polar bonds are not able to cancel each other out. So now what we need to do is look at pretty much all those other molecular geometries to identify how we know if they're polar or not. So for trigonal planar, let's look at two things. Let's start by looking at BF3. Now, this one you could do the vector addition. I'm not going to go through it, but if that's helpful for you, you could do that. But let's just think of the tug of war. This is planar, so it's all in the XY axis. And you've got fluorines, equal strong things, in kind of this pie shape, right? So they're all pulling on those electrons, but they're doing it in equal and opposite directions. So they cancel each other out, and the molecule ends up being nonpolar. So CH2O, which I think we've drawn before, very similar. It has a trigonal planar geometry, but this oxygen is much stronger than those hydrogens. In fact, those hydrogens are probably not going to even attract the electrons from the carbon very much. So similar geometry, but you've got this, if we look at our like 3 steps that I wrote down, we drew the Lewis structure, we looked at the molecular geometry, we do have a polar bond, but they're not equal in strength. So they're not going to completely cancel each other out because these guys are not doing nearly the work or the pulling of that one. So this one would be polar. You have polar bonds, they're arranged in a way or they have different strengths such that they can't cancel out each other. That's when you're saying it's going to be polar. All right, tetrahedral is where we start to get into. Now we're having a Z component there, and so it gets a little bit confusing. Okay, 3-dimensional. This is why I want you to be able to picture what tetrahedral looks like. Biggest, most common mistake I've seen is that people think of, let me do this example in a second, but let's pretend this one we're looking at is CF4, okay? So the white ones are fluorines. Although it may be a little bit harder for you to understand, I think if you play with your intuition a little bit and think of those as 4 things of equal strength in these positions, you're probably going to see that they're able to cancel each other out in the sense that there's not going to be any one side that's going to win in this tug of war. It's a little bit harder for us to imagine because that would mean we would have to have like, the thing in the middle would be floating up in the sky and these ones would be tugging from there. That's why it's difficult for us. A tug of war is usually 2-dimensional in the sense of it's on the ground. All right, once we replace one of those bonds with a lone pair though, now we've offset that geometry, so this would be like NF3. We've offset that geometry. The fluorines are all equal in strength to each other, but there's nobody counteracting them on that top end because there's just a lone pair there. So this would be a trigonal pyramidal geometry. There's no way to make this nonpolar if you have a trigonal pyramidal geometry because you have that lone pair there offsetting things. Now in this example, we thought of CF4. What about though if it was like CF2BR2? If you just drew the Lewis structure, since we're having tests on Lewis structures, I should always go ahead and draw in the lone pairs so people don't forget that they're there. If you just looked at the Lewis structure and did not consider that in 3 dimensions, I guarantee there would be people that would say, oh, it's nonpolar because the bromines are directly across from each other and the fluorines are directly across from each other, so they should all cancel out, right? Well, 4 groups are not arranged in 90-degree angles. They are arranged like this in a tetrahedral shape. So if I have that and I say, these 2 guys up here are bromines and these ones are fluorines, yeah, they're all arranged in a way that if they were equal strength, they could cancel. But bromine and fluorine are not in equal strength. And so there is going to be kind of an overall negative charge down by those fluorines because they are much better at attracting the electrons than the bromines are. So be sure that you don't just draw the Lewis structure and think two-dimensionally. You need to think about how they're actually oriented, and that's why we talked about molecular geometry. So this table kind of neglected to include that. That was only considering that all the external atoms were equivalent. So this one would be nonpolar. This one, however, would be polar. That's a common mistake, is people will just try to memorize, like, oh, if it's tetrahedral, it's nonpolar. Well, right, but only if all the atoms are the same. Same thing over here. Trigonal planar is nonpolar if all the atoms are the same, not if they're different electronegativities. All right, anybody want to ask anything before we keep going? Mm-hmm.
Not an axe, it's really funny if you imagine that as a person trying to walk dogs.
Yes, I like that. And it's like, do you have a Chihuahua or do you have a Great Dane?
And then it makes a lot more sense, because then you have, like, you know, these little leashes going off and they're like dogs. I suppose you need to give the dogs wings when you get three-dimensional them.
Yeah.
Can you imagine how terrifying flying dogs would be? That's not ideal. Like, you have them, like, lift their leg from, like, 5 feet above you. Like, it's really unfortunate.
All right. I like the dog analogy, though. All right. So, like I mentioned before, this chart, this info sheet here, is considering that all the external atoms are the same. So let's go with that. Let's not look examples where you've got an oxygen and a hydrogen, or a bromine and a fluorine. Let's just think about them as all being the same, okay? So we're taking this chart that's from the exam equation sheet, and we're making sure X is always the same thing. It could be fluorine, it could be chlorine, but it's always the same. It's not X and Y, all right? So if we look at this, we said that this guy's nonpolar. We just did an example of that, CO2. This one, BF3, nonpolar. CF3, nonpolar. Hopefully you're starting to see a trend there, that if there is not a lone pair on that central atom, and if all of those external atoms are the same, by definition of how atoms arrange themselves, those will always be nonpolar. Obviously, this is not true if I replace one of those X's with a Y. They all have to be equivalent bonds. But the fact that they orient themselves the way that they do to separate themselves as much as possible means that those bonds are oriented in a way to cancel each other out. So we'll just look at 5 and 6 groups. So here was 4. Here is 5. It's pretty much like having a linear combined with a trigonal planar. And then 6, those are all directly across from each other. It's like having 3 linear things combined. So if there's no lone pair on the central atom and all those external atoms are the same, it's not polar. Once you throw in a different atom, then, you know, all bets are off.
Are we going to have to go all the way up to, like, the octahedral?
Octahedral, yeah. So I don't know why that's not in table 1.11.
Okay.
I give you all of these names, though, and I feel like it is in the text.
It is.
It's in the textbook, but they don't put it on the table for some reason. Okay. I don't know why. So I give you all of the names of the ones for 5 and 6 that do have lone pairs, just because it's like one less thing to memorize. But yeah, you do need to be familiar with them and understand the polarity and stuff. Okay, there's this common misconception, because we did already say, like, the bent ones would be polar, right? We did water for, the bent ones. We did water, and then we looked at, I think SO2 I said. So 3 groups, 2 of which are bonds, or 4 groups, 2 of which are bonds. We also looked at, I said NF3, it could be NH3. That would also be polar. Once people see this, they're like, oh, if there's a lone pair, it must be polar. No. If only it were that easy. If you look at this guy, which I will keep doing the simulation for a little while so that we, what did it have? 2 bonds and 3 lone pairs? Yeah. So those 3 lone pairs are all in that trigonoplanar plane, but then the 2 atoms are linear from each other. Okay? So those will be able to cancel each other out, and this guy will be nonpolar. So you really have to be able to look at this table and visualize what they actually look like. So these dashed lines are meant to be going into the paper, and the solid ones are meant to be coming out of the paper. It's a very common organic chemistry thing. So being able to look at it in 3 dimensions on the simulation and then look at it here and equate the two, that's what I was saying about using the simulation over the weekend as you're studying. Eventually you won't have that, but if you train your brain to think, oh, that's to represent a plane, 120 degrees apart, then it's going to start to connect, and you can just use this table to help you visualize it. Back to the others that are 5 groups. So this one, that would be polar. You've got the 2 that are right across from each other that would cancel, but then you have that odd one out. And seesaw, 2 across from each other, and the 2 that are in the bent shape. So you see the same shapes reappearing over and over. So those ones would both be polar. Again, if they're all able to cancel out, that's when it's nonpolar. And by all, I mean all of those polar bonds. Hopefully you're starting to be able to visualize these. Those 2 lone pairs, when I just boxed out, those are directly across from each other. The lone pairs are linear. I'm going to keep showing you. 2 lone pairs and 4 bonds. And the 4 bonds are all like 2 sets of linear across from each other. So that would be nonpolar. And then the last one over here, they've kind of flip-flopped. So now the bonds are across from each other, and the lone pairs are the things that are in that plane where they're 90 degrees apart. So that would also be nonpolar. But 3 bonds is T-shaped again. 4 bonds is like 2 sets of linear and 1 that's kind of off by itself. So both of these would be polar. So do not just try to memorize NP, P, NP, PP, NP, PP, NP. You're not going to be able to keep that straight. I guess if you had a photographic memory, you'd be good. But the rest of us, not so much. Okay, last 5 minutes. We're going to look at each of these molecules that we've already drawn before. So we already have a good Lewis structure. So we shouldn't have to go too far. I'm just going to go back and forth between the simulation instead of just drawing the Lewis structure. You can go back in your notes. We have all of these in the notes. Every single one of these is going to have polar bonds. So the question we're really asking is, do those polar bonds cancel out? And for that matter, they're all going to be equivalent. There's another table we'll do as kind of a warm-up on Monday. All of these have polar bonds. They're all equivalent. The question is, do they cancel each other out? So NH3 looks like this. So no, they cannot cancel each other out. What just happened? Oh. Can the bonds cancel? CCl4 looks like that. No lone pairs, 4 groups. So this is going to be nonpolar. NO plus, really boring because now we're just going back to like a single bond. Not single meaning single, double, triple, but a bond between 2 atoms. So there's definitely not any canceling out going on there. CO3 2 minus looks like this. That double bond does not matter as far as are they equivalent because it's not really a double bond. There are 3 resonance structures, so each one of those is like a bond and a third, and so they're actually all equivalent. Also, they're all oxygens, so they all have the equal electronegativity as well. So this would be nonpolar. SF4 and SF6, we did those on the video, on the notes. SF4 looks like this. It has a lone pair on that sulfur. So that one would be polar. Oops, didn't mean to do that. This one would be polar. SF6, no lone pair, just that octahedral shape. So that would be nonpolar. Okay, so like I said, try to get as caught up as you can. Do as much of the Chapter 11 homework so that all you're focusing on next week is wrapping it up and then practice exams and studying. It'll be a little bit busy, but if you do a bunch this weekend, you know, it's not going to feel crazy. All right. Enjoy.
I do really like open
Lily, I'm sure I can Google it and figure it out. You don't have
That's what I was
to.
thinking. It's
Yeah.
like, now I want to know for my own gain.
I know.
It's like now you have me intrigued. Though. Like I have to figure this out.
Instagram, real text.
Did you pass the attendance sheets?
Oh, no, I forgot to do the attendance in both classes, so don't worry about it.
I did the little silly pictures to help me visualize it. I thought you might appreciate them.
Wait, there's only 1 dog. Oh, 3 dogs. Okay. My dogs are pretty much the same strength. They pretty much the same.
I have one dog who wants to go back home, and I have another dog who's terrified of the Roman cars. So they're also bigger than me.